Let's look at a standard enterprise security perimeter. It is highly effective at identifying and deflecting brute force attacks. But when a sophisticated threat masks itself within a trusted profile, that same perimeter will pull the payload right into the network. For years, the foundational assumption of enterprise email security has relied on protocols like SPF, DKIM, and DMARC. These systems are designed to automatically block spoof domains and ensure the sender is exactly who they claim to be. Yet, threat actors are currently bypassing these Tier 1 checks completely, and they are doing it without spoofing a single domain. Instead of faking a trusted source, attackers are renting and weaponizing a legitimate one. They are using Google's own application integration service to build workflows that send malicious payloads. This creates a paradox for secure email gateways. Because the malicious email physically originates from actual Google servers, traditional security systems mathematically authenticate the threat as completely safe. To understand how this zero detection campaign works, we need to reverse engineer the attack by tracking a single packet from its origin to the final payload. The operation begins inside Google's cloud environment. The attacker configures a custom email workflow entirely within Google Application Integration. This setup generates a highly specific, legitimate sender address, noreply-application-integration@google.com. To maximize credibility, the attacker pairs this authentic origin address with the standard recognizable formatting of a Google notification, like a file share or voicemail alert. By operating completely within Google's tenant architecture, the attacker weaponizes the platform's trusted reputation to establish a perfect cryptographic disguise. Let's observe what happens when the attacker's email arrives at the target organization's secure email gateway. This flowchart maps the initial inspection as the incoming packet hits the outer perimeter. The gateway immediately splits the traffic to run 3 standard protocol checks. First, the email passes the Sender Policy Framework, or SPF, check. The origin IP address legitimately matches Google's published DNS records. Next, it easily clears Domain Keys Identified Mail, or DKIM. The packet's cryptographic signature is legitimately signed by Google's actual private key. Finally, the email passes DMARC. Both the SPF and DKIM checks perfectly align with the authentic@google.com domain. The gateway registers these successful checks, categorizes the payload as safe, and delivers it straight to the end user. This exposes a systemic vulnerability in how we handle incoming traffic. Our perimeter defenses inherently trust the domain authority itself, completely oblivious to the malicious tenant abusing that authority from the inside. The focus shifts to the user, looking at a seemingly legitimate Google notification in their inbox. Once they engage, the enterprise relies on a second layer of defense, URL inspection and link reputation filtering that triggers the moment the user clicks. Looking at this second flowchart branching from the inbox, we can see the attacker's embedded URL strategy. Instead of pointing to a newly registered or suspicious site, the link directs to Google-hosted domains like storage.cloud.google.com. URL scanners evaluate this and allow the connection because the Google storage domain carries a pristine, highly trusted reputation score. Prompted by the user's click, the network traffic leaves the secure corporate environment. We can track this traffic as it bounces from the Google storage domain through an intermediary Amazon Web Services node. The architectural purpose of this multi-hop routing is evasion. It prevents automated security crawlers from reaching and analyzing the final destination. By daisy-chaining trusted Tier 1 cloud environments together, the attacker achieves complete transit invisibility. At the end of that redirect chain, the traffic arrives at its final destination, a perfectly legitimate Microsoft 365 login screen. Assuming the original Google notification was real, the user proceeds to enter their credentials directly into the authentic Microsoft portal. This brings us to the final safety net most security teams rely on, multi-factor authentication. For a standard user, the credential harvesting mechanism is straightforward. The attacker captures the typed password in real time, while simultaneously letting the legitimate Microsoft login flow confirm that the password is valid. This creates a critical failure point for MFA. The victim receives the MFA prompt on their own device and completes it on the legitimate website. Because the legitimate site processes the authentication directly, The attacker doesn't even need to proxy the MFA token to validate the session. Multi-factor authentication is entirely neutralized when the user is tricked into authenticating against a legitimate service on behalf of the attacker's hidden session. The severity of this exploit scales drastically when the victim holds elevated Azure administrator privileges. For these privileged targets, the payload is an advanced attack vector known as OAuth consent phishing. During the login flow, the administrator is presented with a specific permission request. This diagram illustrates the prompt, showing a JSON code block requesting a very specific management scope. This highly technical prompt is actually asking the user to grant a third-party application direct access to their core cloud resources. The moment the administrator clicks Accept, that malicious application becomes permanently bound to the organization's Azure environment. From a technical standpoint, the attacker now possesses persistent access and refresh tokens. These delegated permissions survive any subsequent password resets the admin might perform. The scope of this access is catastrophic. The attacker can now manipulate Azure subscriptions, virtual machines, and internal databases at will. This illicit consent grant scales a single, simple login mistake into a persistent, infrastructure-wide compromise. We can now look at the complete multi-cloud architecture of this attack, from the initial email send all the way to the final Azure compromise. This end-to-end flowchart maps exactly how the exploit scales across different cloud environments to bypass our existing security assumptions. The first critical defense failure occurs here at the perimeter, where the secure email gateway inherently trusts the incoming sender domain. The second failure happens at the network edge. The URL filters inherently trust the reputation of the hosting environment over the actual destination. The third failure is human. The victim's trust in the initial notification weaponizes the MFA authorization flow against their own tenant. Threat actors have mapped the interconnected trust of multi-cloud infrastructure and systematically used it to neutralize our standard technical safeguards. With the vulnerability mapped, security operations and IT infrastructure teams can deploy specific mitigation strategies against this vector. The first technical step is adjusting gateway rules. Organizations must configure systems to flag or quarantine all emails originating from no-reply-application-integration at google.com for manual review. Second, teams should configure SIEM alerts to detect traffic patterns involving sites.google.com or storage.cloud.google.com, specifically when those links are paired with urgent security or financial subject lines. Finally, human mitigation requires a training update. Internal awareness programs must explicitly teach employees that perfectly authentic at google.com senders can still deliver malicious payloads. As attackers increasingly rent Tier 1 infrastructure to mask their operations, security teams must recognize that domain authority is no longer a proxy for safety. Strict zero-trust principles must now be applied even to the Internet's most reputable domains.